How can you understand Dirac notation with simple quantum examples? Imagine trying to understand a new language that describes the tiniest particles in the universe. That's what Dirac notation does for quantum mechanics. It's a compact way to write and think about quantum states and their relationships. To get a grip on it, start with its basic building blocks. A ket, written as psi, is like a label for a specific quantum state. Think of it as a way to name a particular condition of a tiny particle. For example, the states 0 and 1 are the simplest states for a quantum bit, or qubit. They are like the 0 and 1 in regular computers but can do much more. The bra, written as phi, is the dual of a ket. It's like the mirror image of the state, used to measure or compare states. When you combine a bra and a ket, written as phi psi, it gives a complex number that tells you how much the two states overlap or are similar. This is called the inner product. Let's look at a simple example. A qubit can be in the state 0, which is like a particle being in the 0 position, or 1, the 1 position. But it can also be in a superposition, which is a mix of both. For instance, psi might be written as alpha 0 plus beta 1, where alpha and beta are numbers that tell us how much of each state is present. These numbers are called probability amplitudes, and their squares give the chance of measuring the particle in each state. Now think about the Hadamard gate, a basic quantum operation. It turns the simple states into superpositions. When you apply it to 0, you get the state plus, which is an equal mix of 0 and 1. Similarly, applying it to 1 gives minus, another superposition but with a different phase. Using Dirac notation, we can write these transformations clearly and see how the states change. To find the probability of measuring a particular state, you take the inner product of the state you have with the state you want to measure. For example, if your system is in plus and you measure in the basis of 0 and 1, the chance of getting 0 is the square of the magnitude of 0 plus. Since 0 plus equals 1 divided by the square root of 2, the probability is 1/2. This simple calculation shows how Dirac notation makes it easy to work out measurement outcomes. Another key idea is the completeness relation. It states that the sum of the projectors of the basis states equals the identity. In simple terms, it means any quantum state can be broken down into a sum of basic states like 0 and 1. This helps us expand and analyze complex states by expressing them in terms of simple, well-understood parts. In practical terms, Dirac notation is everywhere in quantum technology. It helps scientists and engineers describe qubits, design quantum gates, and predict measurement results. It's like a universal language for quantum information. By practicing with these straightforward examples, you can build a solid foundation. You'll see how abstract quantum ideas turn into clear, mathematical expressions that guide real-world quantum devices. Understanding these basics opens the door to exploring more advanced quantum algorithms and systems.